All right, let's dive into something that's not just a cornerstone of algebra, but, it's kind of like a secret language for how the world actually works. Linear equations and inequalities. And I promise, by the end of this, you'll see how a super simple idea of balance can solve some really complex problems. So think about this for a second. What on earth could a simple balance scale, your own personal budget, and a high-stakes math competition all have in common? Well, the answer is this incredibly powerful tool that helps us make sense of fairness, of limits, and of finding solutions. And that tool is the linear equation. Okay, let's dive into this. Here's our game plan. We're going to start with a really intuitive game of balance. Then, we'll get into the actual rules for solving these things. After that, we'll turn the algebra into a picture you can see, connect it all back to real life, and then we'll see if you're ready for a challenge. First up, the fair balance game. Seriously, before we touch any formal math, we're just going to build our intuition with a simple idea that pretty much everyone can get right away. At its core, a linear equation is nothing more than a perfectly balanced scale. It's all about fairness. Whatever you've got on the left side has to be exactly perfectly equal to whatever's on the right. Simple as that. Okay, so let's see this in action. Imagine you've got this scale. On one side, there's a mystery weight we're calling x, plus 3 more. On the other side, a weight of 7. It's balanced. Now the trick is to keep it balanced. To figure out what x is, we take 3 off the left side, which means we have to take 3 off the right side too. And just like that, you're left with the solution, x has to be 4.
But, what happens if the scale isn't perfectly level? Well, that's where inequalities come into play. See, an equation is strict. It gives you one single answer. An inequality, though, it's like a tipped scale. It tells you one side is heavier or lighter, which opens up a whole range of possible answers.
All right, so we've got the basic idea of balance. Let's move to the next step and see how this builds into our algebra toolbox, a set of really powerful rules that'll let us solve pretty much any linear equation. Let's try this one. 3x minus 5 equals 10. Our mission, as always, is to get x all by itself. So first, we got to get rid of that minus 5. We do that by adding 5 to both sides. That keeps it balanced and leaves us with 3x equals 15. From there, it's easy. Just divide both sides by 3, and boom, x equals 5. And it's always a good idea to plug that 5 back in just to be sure. And yep, it works. Okay, now, what's really interesting about this slide is that it's probably the #1 mistake people make with inequalities. This is the golden rule you have to remember. If you ever multiply or divide both sides of an inequality by a negative number, you absolutely have to flip the sign. It just completely reverses the whole relationship. Let's watch that flip happen in real time. We've got negative 2x plus 4 is less than or equal to 8. Okay, first step is easy. Subtract 4 from both sides. No big deal. That leaves us with negative 2x is less than or equal to 4. But now, here comes the critical moment. We have to divide by negative 2, and we flip the sign. So our final answer is that x is greater than or equal to negative 2. See how that works? So far, this has all been about numbers and symbols on a page. But what if we could actually see what these equations look like? Well, we can. That's our next section, turning abstract algebra into a picture. Graphing an equation like y equals 2x plus 1 is almost like following a simple map. That plus 1 at the end, that's your starting point. You just go to 1 on that vertical y-axis. Then, the 2x part gives you the directions. From your starting point, rise up 2 and run over 1 to the right. Do that a couple times, connect the dots, and there you have it, a straight line that is the picture of that equation. And you know what? Graphing an inequality on a number line is even easier. Let's say we have x is greater than 1. Okay, so you draw your number line, you find 1. Now because it's greater than and not equal to, we put an open circle there. It's like saying, hey, we can get super close to 1, but we can't actually be 1. Then you just shade everything to the right because all those numbers are greater than 1. That whole shaded area is your answer. Okay, we've got the mechanics down, we know how to solve them, we know how to graph them, but why does any of this matter? Well, it turns out this is a skill you are probably already using every single day, maybe without even realizing it. Seriously, think about it. Anytime you've ever set a budget, you were doing algebra. The moment you say to yourself, I can spend at most 500 rupees, what you're really saying is that your spending has to be less than or equal to 500. And right there, that's a real-world linear inequality. And it goes so far beyond just budgeting. This is the math that calculates the arrival time on your GPS. It's used to model how things move in physics. It's how businesses analyze profit and loss. It's literally a fundamental language for describing how the world works in straight lines.
So we've built a really solid foundation. We have the tools. Now I think it's time we put our new toolkit to the test and see how these simple rules can help us crack some tougher problems. Ready?
Okay, here's a problem you might see in a competition. Now, when you see something like this, the first step is always just to clean it up. Let's distribute that 2 on the left side, which gives us 6x minus 2. Now that looks a lot more familiar. From here, we just collect our terms, subtract 5x from both sides, add 2 to both sides, and we find our solution. X is less than or equal to 6.
Now let's try an expert level one with these absolute value bars. They can look intimidating, but just remember that absolute value really just means distance from 0. So what this is really saying is that the thing inside, the 2x minus 1, is less than 3 steps away from 0 on the number line. That means it must be trapped or sandwiched between -3 and 3. So we can just rewrite this as a double inequality. -3 is less than 2x minus 1, which is less than 3, and from there, you just solve it like you normally would. So the crucial point is that as you get into these more complex problems, it's really easy to make a simple mistake. Think of this table as your mental checklist. Before you circle your final answer, just ask yourself, wait, did I divide by a negative? Did I forget to flip the sign? Or did I plug my answer back in to check my math? For graphs, try testing a simple point like 0. These little checks will save you so many times. So, there you have it. We started with a really simple idea, a balance scale, and watched it grow into this powerful tool for solving problems and actually modeling the world around us. That's the real magic of math. So my last question for you is this. Now that you know what to look for, where else in your world do you see the hidden logic of a straight line? All right, today we're putting on our detective hats. We're on a mission to crack a code. But this code isn't hidden in some secret message. It's hidden inside a couple of simple math clues. And trust me, this is way more than just a numbers game. This is the key to solving real problems in physics, economics, and a ton of other fields. So let's dive in. Okay, so picture this. There are 2 secret numbers, and I'm not going to tell you what they are. Not directly, anyway. Instead, I'm going to give you 2 clues. And your job, as the detective, is to figure out the one and only one pair of numbers that makes both of my clues true. You ready for this? Here are your clues. Clue number 1. If you take the first secret number, double it, and then add the second secret number, you get 5. Got that? And clue number 2. The first number minus the second number is just 1. Now, somewhere out there's a single pair of numbers that fits both of these rules perfectly. Now, these clues, they've got a fancy name. In the math world, we call this a pair of linear equations. It sounds complicated, but it's really not. It's just 2 rules about the same 2 unknown things. We usually call them x and y. Our entire goal here is to find that one special value for x and that one special value for y that makes both rules true at the exact same time. So how do we actually crack this code? Well, lucky for us, we've got a whole toolkit with 3 really powerful methods we can use. We're going to walk through each one, starting with the one that lets you literally see the answer, and then we'll get into 2 super clever algebraic tricks. First up in our toolkit is the graphical method. This one's all about seeing the solution. We're not just crunching numbers, we're going to draw a picture of our clues and see exactly where they lead us. The core idea here is actually super simple, and it's kind of brilliant. Every linear equation, like our 2 clues, can be drawn as a perfectly straight line on a graph. So if we draw the line for our first clue, and then draw the line for our second clue, the single point where those 2 lines cross, that's our answer. It's the one spot in the entire universe that's on both lines at the same time. Now, think about it. If you draw any 2 lines on a piece of paper, what can happen? Really, only 3 things. 1, they can cross at a single point, which gives us that one unique solution we're looking for. 2, they could be parallel, like railroad tracks, and never ever touch. That means there's no solution. Or 3, they could turn out to be the exact same line, just one on top of the other, which means there are infinite solutions. Okay, let's try it with a fresh example. Our first clue is x plus y equals 4. We can draw that line. Our second clue is x minus y equals 2. Let's draw that one too. Now all we have to do is look. Where do they meet? And boom, right there. The lines cross at the point 3, 1.
That means our first secret number, x, has to be 3, and our second number, y, has to be 1. It's so cool, because you can literally see the answer to the whole puzzle right there on the graph. Okay, on to tool number 2. This is for when you don't have graph paper lying around. It's our first algebraic tool, the substitution method. Think of this one like a clever swap. We use one clue to figure out a secret about one number, and then we use that secret to crack the other clue wide open.
So here's the game plan. We're going to look at one of the equations and just rearrange it a bit to get one of the letters all by itself. For example, we might figure out that y is really just another name for 5 minus x. Now we have a secret identity for y. So we take that new identity and we substitute it into the other equation. All of a sudden, we have an equation with just one variable, and that is way easier to solve.
Let's walk through this one together. Our clues are x plus y equals 5 and x minus y equals 1. So step 1, let's take that first clue and get y by itself. A little rearranging, and we get its secret identity. Y equals 5 minus x. Step 2 is the substitution. We're going to replace the y in the second clue with this new identity. So x minus y equals 1 becomes x minus, and be careful here, the whole quantity, 5 minus x, equals 1. Now for step 3, we just solve it. A little algebra that simplifies to 2x minus 5 equals 1, which means 2x equals 6, so x must be 3. And finally, step 4, we use that answer to find y. If we know x is 3, we just plug it back into our secret identity, y equals 5 minus 3, so y is 2. And just like that, code cracked. The solution is 3, 2. We didn't need a graph, just a bit of clever substitution. The whole trick, the real key insight here, is that we turned a tricky 2-variable problem into a super simple 1-variable problem. And that's something we can totally handle. All right, on to our third and final tool, and honestly, this one might be my favorite. It's a real power move called the elimination method. This technique is fast, it's elegant, and sometimes it feels a little bit like magic. The idea behind elimination is just so cool. Instead of working with the equations separately, we're going to combine them. We'll either add them together or subtract one from the other, and we'll do it in such a clever way that one of the variables gets completely canceled out. It just vanishes. You know, the source material puts this perfectly. It says you're combining equations so one variable cancels, like magic with balance. And that's exactly it. Because each equation is a true balanced statement, we can add them together, and the result is still a true balanced statement. It's that principle that lets us make one of the variables just disappear. Okay, check out this example. It is practically made for this method. Notice how the first equation has a plus 3y and the second has a minus 3y? They are perfect opposites, just waiting to be eliminated. So, what do? We just add the two equations straight down. The 2x and 2x combine to make 4x. The plus 3y and the minus 3y, they cancel each other out. Poof, gone. And 11 plus 1 is 12. Suddenly we're left with the super simple equation 4x equals 12. Well, that means x has to be 3. How easy was that? So we've been finding solutions left and right. It's been great. But what happens when the clues are just bad? What if they contradict each other? Or what if one clue is just the other clue in disguise? These are what we call special cases. So how can you tell what's going to happen without even drawing a graph? Well, there's a neat little trick for that. It all comes down to comparing the numbers in front of our variables, the coefficients. Imagine our equations are written out in a standard form. This table is basically a cheat sheet. By comparing the ratios of the numbers in front of the x's, the y's, and the constants on the other side, we can instantly tell the outcome. If the first two ratios aren't equal, you're golden. The lines intersect, and you've got one solution. If the first two ratios are the same but they don't match the third one, the lines are parallel. No solution. And if all three ratios are exactly the same, well, then it's just the same line twice, and you've got infinite solutions. It's a really powerful way to connect the algebra back to what we saw in the graph. All right, you've seen the whole toolkit, you know the moves, you've seen the shortcuts, and even what happens when things go wrong. So, you ready for a quick final test? Okay, mission time. Your job is to solve this system. X plus y equals 6 and x minus y equals 2. I'll even give you a little hint. Add them together. It's set up perfectly for elimination. Go ahead, give it a shot. I'll wait. You got it? The answer is x equals 4 and y equals 2. So yeah, we cracked the code. But here's the thing. This is so much more than just a math trick. This is a blueprint for problem solving. I mean, think about it.
In business, you're looking for the break-even point where your cost line intersects your revenue line. In economics, it's about finding where the supply curve crosses the demand curve. So I'll leave you with this to chew on. What other real-world problems can be solved by finding that one precise point where two different rules intersect?